Okay, we've just finished the quiz, and I got asked a question about what is a pulse train, and we've been talking about pulse trains, but we have that over here in our Jupyter notebook too. So the pulse train is a signal that you spend a lot of time on in lab 2, but it's a radar type signal, so it's kind of a fundamental waveform that gets used in applications of that sort. So I actually created a function here in the notebook called pulse train, and all the pulse train function does is it just replicates a rectangular pulse up and down the axes, and I did it kind of in a novel, creative way using a mod function. So you might want to study this sometime. You might want to study any of the code that you've seen in Python, and if you like coding, which I think it's pretty much in everybody's future that you're going to be doing some kind of coding, there's always the desire to make something kind of fast and efficient. But fast and efficient can be the hardest to understand, and this is an example of something that may not make a whole lot of sense, but what I'm doing with the mod function, I believe, because I haven't looked at this for a while, is I'm looking at when both of those conditions are true, then I will set the value equal to 1, and when they're not true, then it will do nothing. And since I've initialized the array to be zeros from the very beginning, then we're good to go. But the mod function, you'd want to study how the mod function works in Python, make sure you're clear on it. So as time marches along, it's going to hit an interval where it should produce a pulse, then it's going to go along where it's going to be 0, and then it's going to hit the next start of the next period, and then it's going to say, oh, I'm modulo in that interval, and it should turn on again, right? And then as time sweeps further on, it's going to go off and then come back on again. There'd be a number of ways of creating it, but this was just the way I did it. So if I do this down here, though, and this notebook reset, so I think I have to rerun this cell, and everything reset. Pulse train is not defined, but yet I just ran the cell, so it should be defined. There we go. So there's an example of a pulse train, and this one was created to match problem 229 is why I created it, was to talk about 229. I gave you a different take on it for the homework. I said generate one period of it, but still the same idea, right? So you were just generating one period of it. But this is a number of periods, however many periods you specify. And it was just for drawing the picture. The line spectra, though, for the pulse train is this formula right here. And if you have a pulse train where T naught, there's no offset on the pulse train, so the first pulse is just centered right at 0, then this term right here is going to be e to the j0, which is going to go away. So then you just home in on this part. I won't say anything more because, I don't want to give anything away, but that's the time 0-centered pulse train. But we know from the theorems in the Fourier transforms that a time skew does not alter the magnitude spectrum. It only alters the phase. And when you're in the lab working with the function generator producing the pulse train and the spectrum analyzer viewing the magnitude in dBm in a 50 ohm system, all kind of wrapping it up to be more realistic there, then you just see the magnitude of this function. So you get the magnitude of the sinc function and then a tau over T naught. And that's what goes on down here. I theoretically get those Fourier coefficients, load them into this variable xn all at once because I've swept n over a range, and my function line spectra, if I was to go shift tab in that, it tells you that what I load into it is magnitude and phase at each positive frequency, and then it takes care of, it makes the assumption it's a real signal, so it takes care of producing the two-sided spectrum using the symmetry properties, is the way I wrote this originally. And then you can put in the x0 value if you want to separately. So this was an exercise where I tweaked things up, and this is what you were finding out in the homework. So since John has already turned his homework in and you guys have already turned yours in, I can go ahead and talk about that since I had that built up in the code right here. So if I comment that line out, my finger's on the right keys. Yeah. Control / automatically puts the comments in and takes them out again. Most code editors do that. You know what I'm talking about.
Yeah, no, Control / is game changer.
There's other game changers out there though too, right? Like selecting and indenting or on-indenting. Python, if you haven't noticed it, Python works by indenting. And it's totally, yeah, so it's all about indenting when you write a Python function, and that's what's going on right up here. But the editor manages that for you. So what you have to do, and you have to learn to relax. Don't fight it. I mean, when I first started coding in Python, I had these indent errors and stuff, and then I just said, I got to get the indents out, so I got all of them out, and then I put them back in carefully with the block indent capability. And then from then on, I try not to mess around and trying to second guess anything. I let the editor just manage it for me because it's trying to do the right thing for you. And that's, unlike C, that's what makes Python a little bit harder to learn at first. See here, that that colon is telling the editor and telling Python that we're going to start a block of code that's going to be a for loop. So as soon as I hit return, it automatically indents me the 4 spaces that are required in Python to say I'm going to start that block of code that's inside that for loop. And then I wanted to have an if case inside of here. I put that colon on the end of this if case, and as soon as I hit return on that, it indents me yet again because it says now we're going into another sub-block of code. And so then when you get done with that, if you're thinking in C, you're saying I have to have a curly brace. Don't have to have so many curly braces to get back out again. But in Python, it's really just a matter of as soon as you come out, and if you're outdented once and then twice, which is what's going on here, then it's like we're back out of both sub-blocks of code. It just knows that's the way it parses the code. So you don't have to put any blank lines in there. You don't have to do anything. You can if you want to, but the way the interpreter knows that you're done is that line of code with the return in it has been outdented all the way back out to the 4 spaces. And everything in the body of the function is indented one grouping of 4 spaces because that's part of the definition of the function, is to say it's a function. And I could have in this code cell, I could come along right here, and I could start writing another definition right in the same code cell, and when I do Shift Enter on it, it will load that function into the memory, and that will be available too. It's really very nice, I think, the way it works. I mean, when you write a module of code, you do the same thing. You can cut these functions out of the notebook cells here, and then you can put them into a separate source file, and that separate source file can then be brought in, like I do at the very top here. You would do an import on it, and as long as it's in the same folder where you've got the notebook, you'd be able to import a module. So I write functions in the notebook as prototypes, and then when I'm happy with them, I'll move them into a module, and then they're sort of wrapped up and are more permanent. More permanent yet would be to put them into the repository, push them to GitHub or something. But you will be working with modules of code in the first and second project, because I'll give you some special code to work with. But most of the time I try to have you work with just the code developed right in the notebook. And don't think of it as a bad habit. It's actually, I think it's a good thing because it's right there. You can see it. If you already committed it to a module, it would be hidden away. But the other cool thing about this environment is, let's see. don't have a launcher running right now, so if I brought up a launcher, I can always open up files, and I could be working on a module of code right here if I wanted to. I could pull it out if it was sitting in here and I don't have one. Well, I guess I do. Test Pi. So there was the start of writing a module for something or another. So I could be working on a module in here too if I wanted to. You picked this stuff up really fast, I think. And you had C programming, and you had an IDE, and you had a project, right? And how many files were in a project? As many as you needed, right? You had to have at least one. And in C, you have to have at least one module that has a main function in it, right? And then you can have .h files, the includes, and all that kind of stuff. Okay. So I answered that question. I'll come back into this notebook, though, later, because right now we are I'm going to take a look at this example in a moment, but I just want to go recap to where we were from last time. We were staring at a white space. There it is. So I'm backing up a little bit. I think we had gone into the convolution theorem, and that's kind of where we stopped. And then I went off and did something in the notebook at that point. So we talked about the convolution theorem for Fourier transforms. I took that problem off the table in the homework to turn in. You'll get a chance to practice with convolution on something down the road, maybe in the next assignment or something. But I wanted to just get it out there. You can see my solutions and get your brain thinking about it. This class is not about doing convolutions in the time domain. It's a very tedious process, right? You've done it, you know it can be done. The type of convolution, though, that you absolutely have to be able to accept wanting to do would be this type of convolution, where you're convolving a function with a delta that's time shifted in some way. So that just uses the sifting property again, and you sift out the functional value of whatever is going on. And you can rearrange these arguments if you want to. You could put a t minus t naught in there for x of t, and you could put delta of t by itself, or you could have one would be shifted by t1, the other would be shifted by t2, and then when you convolve them, you'll get the combination of the two. So this type of convolution is a no-brainer, right? And you don't balk at that. Say, I will gladly do that convolution, because it's not hard. So I did put this example in. We talked about the results of this one. Then this is the convolution theorem, which follows from understanding what convolution is, just saying that when you convolve in the time domain, you multiply in the frequency domain. And that is very powerful, and it shows up a lot in comm systems. If you really want to get intense about getting back to the time domain again, you're better off working in the S domain, though, because then you can use the Laplace transform, the inverse transform, once you get back, and when you want to get back to the time domain. And that you practice that in 3205 and, well, 3205 mostly, I think. And we will see that when we study phase-locked loops. But for us, it's what's going on in the spectral domain. So if we're convolving signals, we're multiplying the spectra. If we're passing a signal through a system, then we're multiplying the input spectrum by the frequency response of the system, because that's the Fourier transform of the system's impulse response. That gets reviewed a little bit later in the notes and in the book, so I don't need to go through that just yet, but that's the idea there. I thought, though, I would at least do walk through this one convolution example, and there's a couple of them here in the notes. So this is convolving a unit step function with an exponential. So the two functions are, one is a step function and the other is the exponential. So when you actually carry out a convolution, you choose not to do it in the frequency domain or in the S domain, but you actually want to do the convolution or have to do the convolution because it's just the best way, the best alternative. You have to think about how do you set up the integrand. So in this particular case, I chose to do a u of lambda, and then in the integrand I put e to the minus alpha t minus lambda u of t minus lambda d lambda. So I chose to do the convolution that way. One argument in the integrand is like x1 of lambda, and the other one's x2 of t minus lambda, so you have to flip it over. So that's the first thing to get your confidence back if you haven't done it for a while or just it drifted out of your brain quickly. This is something that has to get set in your brain fairly well to really have endurance to last. So in this case, I chose to keep this one fixed. So that's this guy right here, and then I have to flip this one. So how do I flip signals on the time in the lambda axes? I will do it usually in steps, but my general approach for doing any flipping like that would be to get your brain set on it. So you have to say if it's going to be u of alpha t minus lambda times u of t minus lambda, the first thing you have to do is establish where does it lie on the lambda axis for t as a parameter. So I look at this function and I know globally that this is active if t minus lambda, the argument, is greater than or equal to 0. Equal to 0 is kind of nebulous because the step function is not defined there, but I'll just say greater than or equal to 0 anyway. So I know that that's where it's active, right? But then how do I plot the function? How do I know that when I plot this function, it sits over here in this orientation? So what I recommend that you do if you're not remembering the best approach, or maybe have it what you think is a good approach, but you're open to try something new, is my approach is very brute force. I just say, okay, I know it's going to be active if t minus lambda is greater than 0. So in terms of the lambda axes, I just simply go down here and rearrange the inequality. So I would move lambda to the other side, so it's going to be for t greater than or equal to lambda. Because I moved lambda to the other side. Or, if you don't like it that way, lambda less than or equal to t. So that's what we have here. This is probably the better way of thinking of it, because this just tells us that's where we're active. So on the lambda axis, we have to have lambda less than t for it to be active, and it's 0 otherwise. So that's telling us where it turns off. If I was flipping over a pulse, though, suppose it was a pulse t minus 1, then it's a little bit more complicated, because then when I put this in the form of pi of t minus lambda, that's my substitution for t, and then I put minus 1 in there, then I have to say t minus lambda minus 1 is going to lie between minus 1/2 and plus 1/2. That's where the rectangular pulse is active, right? And then if I want to figure out on the lambda axis where it's active, I have to go down below here and say, okay, I have to move lambda to the opposite side, so I'll do that in this sense. I'll move lambda to the opposite side, so I guess I should erase that. Move lambda to the far left side, so lambda less than or equal to t plus 1/2 and minus 1, which equals t minus 1/2. And then the other inequality is going to be when I move lambda over to the far right-hand side, it'll be for lambda greater than or equal to t minus 1/2 minus 1, which equals t minus 3/2. So then I can summarize what's going on there, and I can say, okay, so that's going to be active on the lambda axis. When lambda is greater than or equal to minus 3/2 and less than or equal to minus 1/2. Well, I forgot something. T minus 3/2. T minus 3/2 and t minus 1/2. Forgot to include the t. So now you see how it's sliding along on the lambda axis, and then you can go ahead and do all this stuff with the limits. But my point being that when you're doing a convolution like this and you have to set up the integrand and figure out the limits, you got to get this part right from the start. Because if you don't, then everything else is just garbage from thence on. Those of you remember that, right? I mean, it's very easy in a convolution integral problem to create garbage, because if you don't start right, then everything from then on is just messed up. When I wrote the Dummies book, the editors knew a priori that was like something that I had to grill and drill on. So I think I did a fairly good job in the book. I had a lot of examples. There's more examples on the internet of how to do that. And then that led me to writing some functions for discrete time and continuous time convolution, which I'll take a look at here eventually. I think there's a better way to delete, but I don't remember what it is for this tool, so I'm doing it the hard way. So at any rate, for this problem, I chose that orientation, and once I have that picture drawn, then I can visualize everything I need to do the convolution integral. So I'm going to integrate from minus to plus infinity. And the first case is when, get rid of this stuff too. First case is when t is less than 0. There's no overlap, so the output, and that should say y of t, is equal to 0. Then as I bring this guy up so that there is some partial overlap, for t greater than 0, so now I know that my limits are going to be when the product of the two waveforms is non-zero, and that sets the limits to go from 0 to t, and then I just integrate whatever I have in my integrand. I'm good to go there. Integrate that out, and I get the answer that I have given here for what y is doing for t greater than 0. And in this particular problem, there's no other case, because as t is greater than 0, there's always overlap. For t can now move out to infinity, and this tail right here is always going back to minus infinity, so there's only 2 cases to do for this one. And from circuit theory, you know that this could be viewed as a step function going into an RC filter, an RC low-pass filter, and the filter is going to charge up as a result of the step function going in. So you close the switch and the circuit charges. That's an analogous thing. And your electrical engineers, even though you may never want to do circuits in your life, because nowadays you don't have to, hardly, if you don't want to, as an EE, those ideas should still be burned in your brain. And even though it's not a circuit theory problem, it's an analogous problem. And in the world of analysis and simulation, you still see things that you can relate back to something that you first learned. I do that all the time. I say, oh, that's like a circuit problem when that happened. I mean, the charge up and discharge, those types of things got loaded in your brain at a young age, and you tend to relate back to things like that. So over here in the Jupyter Notebook, if you have to do a convolution, I've got it written out in here, but I do have a function called conv integral that can do a numerical version of a convolution. So here I just chose to convolve 2 rectangles, one of width 1, the other of width 3, and then I loaded into the convolution integral function. And the way I created this function is that you put in the first function in your convolution, and then you have the corresponding time axes that you created to go with it. And then you put in the second function and put in its time axes. And then I have this little special extra argument, optional argument, where you get to set whether the first function is a finite extent or left-sided or right-sided, or the second function is finite extent or left-sided or right-sided. And all that means is numerical convolution, if you don't give it the right time axes, it can give you a bogus answer. I'm just curious, has anybody ever run into that earlier in another class like 2610 or 3205, where you thought you were going to numerically do a convolution and then you got an answer that looked wrong? Has that ever happened?
I think so.
You don't, you wouldn't know.
Started happening last semester in DSP for probably a couple hours before I figured it out.
Okay. Well, what I did when I wrote this function, since it was written for the Dummies book, I decided I needed to do something to make sure that if part of the extent was going to be, part of the output was going to be invalid because of incomplete information, that I would limit the convolution integral from displaying everything so that you wouldn't see something that's bogus. It's an artifact of the simulation. And what makes a simulation go bad for a convolution is if you've got something that's of infinite extent, either going right out to the right or all the way back to the left, and you don't give it enough time axes to actually do the convolution with, part of the time axes is going to, part of the output is going to be incorrect because the waveform doesn't go to infinity, and if you try to look at too much of that output, it will eventually go away, and you know that that's not really true. The example we just looked at is a good example of that, where it does have infinite extent. So in a simulation, if you drive it too hard, what will happen is this will just go away. So I try not to display that by putting the extents option in there in the Python code. Most of the time it's finite, or frequently it's finite, so here I just left it at the default value of f, which doesn't have to be loaded in. It's an optional argument because it's been set equal to something already. But there's other cases where that's not true. I'm not really going to go into it to a great extent, but I did do an example here where I took exactly a function kind of similar to what we're looking at, only I took a rectangle pulse and then convolved it with an exponential decay. So I made use of the extents. I said the rectangle is finite extent, and the exponential is a right-sided sequence. It goes off to infinity. And then I set it to convolve that. But if I wanted to modify this problem, I haven't played with this for a while. It's probably dumb that I'm doing it, but maybe you'll be intrigued about something. So I'm just making a copy, and I'm going to comment that line out, and then rather than doing a rect, I'm going to make this a step, and I'm just going to put the time axis in there, tx for both the x and the other pulse value, the exponential decay. So that should work. And that matches the answer I would expect from the theoretical result over here. But I think if I told it that this was finite extent, see what it did? So this was to protect the innocent, in a sense. I mean, if you get my drift on the dry humor side there, this is not correct, right? Your brain would say, wait a minute, it goes away, but so it's going away at about 8, it looks like. So essentially all that I'm doing when I say it's right-sided is it's not going to go beyond the point where it goes away. So I have this output support interval that gets displayed that tells me this is the only interval I can trust to get the right answer. Outside of that, no deal. It could be wrong. So I did that for my audience, but honestly, I don't think my editor, I thought it was a very novel thing because I just wanted to make it more robust, but I don't know if anybody's ever made use of it or not. Since we're in Python right now, and I do want to move on to the other stuff, I'll just say that there'll be some times when we might want to do a simulation with a band-limited signal. So last time we talked about how from duality, if you Fourier transform a sinc function, you get a rectangle. So let's just kind of take a look at that. We have the function that you've already been playing with, Fourier transform approximation, which inside, I didn't really explain it, but inside it's using the FFT. No surprise there, but I'm trying to make it like a little bit of a black box. You just are working with a finite extent. So what I do here is I generate the sinc function over a certain interval of time, and I plot it. And it looks like I've got a pretty good interval. It's tapering off, but it's still getting truncated. It doesn't go from minus to plus infinity because I have to say I'm only going to represent so much of that sinc function. So then I use the Fourier transform approximation function with 4096 points, and there's what the spectrum looks like. So it obeys the right property. The only problem is because I've truncated the sinc function, I have the same problem that exists for Fourier series, namely that if you're trying to get the Fourier series, trying to synthesize a Fourier series from its coefficient, you always get ringing on the edges of the square wave or pulse train. It's called the Gibbs phenomena, and it's because Fourier series, although you can synthesize any periodic signal, one shortcoming of the Fourier series is it does not converge pointwise everywhere. At points of discontinuity, it fails to work properly. It has this ringing problem, and then near that discontinuity point, it has this ringing. So I did it in dB, and when you talk about digital filter design, which I'll maybe talk about at some point, Chris saw this in modern DSP, but it happened really at the end of the semester. The first side lobe is down only 21 dB from this flat spot. We can't just build a brick wall filter. The end of the basic story is here, you can't build a brick wall filter by just truncating a sinc function and saying it's going to be a nice perfect brick wall filter, because it has this ringing in it, and the fact that the side lobes are only, the first one is only down 21 dB and then it drops off at that rate, that's not really good enough to call this spectrum truly band limited. Linear plot, it looks fairly believable, and the dB plot, which tells all in my opinion, which is why in the lab it's so much fun to use the spectrum analyzer, because the spectrum analyzer puts it in dB naturally, and that's what you really want. You really want to see how not good it is. I could say how bad it is, but you know what's really going on at the low level. But this is still useful in some modeling purposes, so there you go. Question?
Yeah, so let me see here, I think. So you put a Gaussian time domain, time function on top of that, that would reduce it, right?
Yeah, the side lobes. You'd put a window on there and that would reduce it.
Okay.
And a Gaussian,
It's pretty smooth though in the
Yeah.
reading.
a Gaussian has the property though that a transform of a Gaussian is another Gaussian. So that's a very special signal. There's 3 signals that have that property that I know of. When I was a PhD student, I learned this as a trick question for students when I taught linear systems back in Missouri S&T. One signal is 0, Fourier transform 0 and you get 0. That's a silly result, but it is true, right? Fourier transform of 0 is 0. The second one is Fourier transform of an impulse train gives you an impulse train in frequency. We'll be talking about that one shortly. Then the third one is the Gaussian. Fourier transform of Gaussian is Gaussian function. Not the exact same shape. I mean, there's a Gaussian bell, but the width of the bell is inverse reciprocal from time to frequency, but still true. This looks, well, okay, since I'm looking at this, how could I make this better? Well, I could actually, just notice if I make this squared, we know that sinc squared becomes what? Remember, we saw this last time. Sinc corresponds to rect in, so this should be the triangle. Let's just play that out. There it is. There's the sinc squared and there's the triangle. I don't really have enough frequency axis that I'm plotting in here to actually see it, but I could open this up by commenting that out. I guess I'm at the full extent though. At any rate, the triangle is a little bit better because it's already had it's effectively a window that's smoother. It doesn't have the discontinuity in it that we're trying to represent. When you have those dull moments, I recommend playing in Python with the mathematics and just trying to you're not learning the notebook as much as you are just trying to see, is this math making sense to me? You can kind of play games and just test your knowledge and say, is this making sense? I do that all the time to this day. If I'm working on a hard problem, I build a little simulation and try to get a real hands-on feel. Is my intuition working? Am I going to be able to go forward with this for my project that I'm working on for somebody? I don't trust the math, my ability to use the math to the infinite extent. I have to model something on the computer to kind of get an idea. Am I heading in the right direction? And I cycle back and work on the math some more. That maybe some people don't have to do that, but I do. I have to see something, I have to kind of feel something, and I really don't like the idea when people say they go into mechanical engineering because they have to touch and feel things. I don't think electrical engineers are that much different. We like to touch and feel things too. It's just we may not be able to put our finger on the individual transistors in an integrated circuit because it's really, really tiny, but we can play with it on the bench with a fixture, and we can model things on the computer and get an idea of properties and things. So I don't know, what do you guys think? Do you feel like there's total lack of hands-on in electrical engineering? I totally disagree, but people that come in think that this is not going to be good for them because it's not enough hands-on. I disagree. You can find it.
Touch the $500,000 spectrum analyzer though. AGE.
The one it's in the anechoic chamber?
Yeah. Don't let it touch the ends of the cables.
The millimeter. Well, static electricity can blow things out. I mean, when I was in
hard time
Well, it's true though. When I was in school, they hardly let us use any spectrum analyzer because they were so deathly afraid that we would blow a front end out on a spectrum analyzer. And now they've made things more robust. But yeah, I'm convinced you guys could blow something up in the lab if you weren't careful. I'm just not stopping you from using it though, because it's pretty important.
I don't know, I'm always curious about all those burn marks in the electronics lab. Like,
Oh, really?
yeah, what happened there? How big of a capacitor was that?
Don't ask.
Oh, I'm asking. I want to beat it.
But maybe somebody had a lighter to shrink some heat shrink around something, and they set it down on the bench, and it was still hot, and it put a scorch mark there, or
Oh,
the
no,
soldering iron.
There's a big one on electronics.
Okay,
There's a full-on divot, like, yeah. No.
okay,
And it's been rubbed smooth from years
okay.
of touching it.
Moving on, the next theorem is the dual of the convolution, and that's multiplication theorem. And we will definitely use that a lot as well, because we frequently will multiply one signal times another, or a communications channel introduces multiplicative noise. So we have things like that. So this dual ends up being useful. We'll see it when we need it, and we will be definitely using it in the following chapter. Now we're going to jump into this topic, Fourier transform in the limit, and this is going to get us integrated with bring Fourier series in. So we already know that periodic power signals have a line spectra, and when you have a periodic power signal, your brain is programmed to say Fourier series. It's going to be a line spectrum. It's like what I see in the spectrum analyzer. Fourier transform has to just stay away from all this stuff, but not so. That's what we're going to look at. And we know if you have a non-periodic, aperiodic signal, energy signal, then it has a nice continuous spectrum. So we're after a unifying approach to spectral analysis. So the first step is to allow impulses in the frequency domain. Allow those delta functions that are somewhat nebulous, allow them to be an idealization of an impulse in frequency. And what makes all of that work is the idea of Fourier transform in the limit. And this is not, mathematicians probably don't like seeing electrical engineers doing this because we're interchanging the order of an integral and a limit, and in mathematics you have to make sure that if you do something like that you have convergence and you have certain smoothness and other good things happening. But we do it in an operational math sense and say there really is no such thing as a delta function. It's just an idealization for mathematical convenience. Notice I say convenience, not mathematical frustration. We do it for convenience. Mathematicians might say it's got to be so dead on precise that you got to study a lot of advanced real analysis to make it be useful. We don't look at it that way, and we use it in probability to represent a probability mass. Physicists and EEs in advanced electromagnetics use 1- and 2-dimensional delta functions to represent charge, distributions, current, densities, and other such things. When I took my advanced EMAG class from the physics department many years ago, I was really impressed at how it expanded my understanding of the ability to use delta functions. And then I've used it in other ways on the EE side too, so it's good. So to get into this, we just move in with some simple examples and then kind of jump and ramp things up quickly. So the first example is just considering a constant signal, just a DC voltage, say A. It's always on, let's say. And we could write that waveform as the limit as t goes to infinity of A pi of t over capital T. So it's just going to be something that just gets wider and wider as the limit goes to infinity, and then it will look like the constant signal. So now we say, okay, this is an energy signal. So we can take the Fourier transform, and it's AT sinc FT, just like we talked about last time. And then we sit back and think about it for a while and say, okay, now we're on the frequency domain side with our sinc function, and now we're going to do what the mathematicians don't like us doing, and that is we're going to take the limit after the integral. We should be taking the integral with the limit on the inside, so it's infinite in duration, but then we can't Fourier transform it, right? Because it has infinite energy and the theorem doesn't work. So the big thing about Fourier transform and the limit is do the limit after you take the Fourier transform of the finite energy signal representation. And when we do that on this sinc function, what we see is that for some value of t1, we get the big blobby sinc function. And then as we take another time value t2, which is much greater than t1, it's getting compressed down. It's getting more focused at f is equal to 0. And then we think about it a little bit and could do some more analysis too. But first off, the sinc function can be used as a test function for a delta function if we normalize it properly. So it turns out can't spell right now. I don't know what I'm doing wrong. A test function for a delta function is just some function that as we take the limit, in this case t, and let it go to infinity, the function will have the delta function-like properties of being 0 everywhere except at 0, having a height that's going to go off to infinity, but having an area that remains fixed or constant at 1. Remember, that's kind of that's how delta functions get introduced to engineers. That's sort of the operational property. And that's exactly what we have right here. And then on top of that, we also sit back and look at this and say, as I let t get very, very large, that delta function is compressing in, and we think, where should the spectral information of a constant signal reside? Should it be spread all over a wide band of frequencies? Given that it's a constant, it should be focused all at DC, right? So the fact that that is common sense, that's this bullet right here. There's no time variation, so the spectral content ought to be confined to f is equal to 0. So what we can then say as a Fourier transform, the limit property is that it's a delta of f. So now we've opened up the floodgate through superposition and other properties of Fourier transforms to do all kinds of interesting things with this. We can take a times a complex sinusoid, and through frequency translation, we're just going to put that delta function spike up at f naught. We can then put a pair of these together, one spinning clockwise, the other one counterclockwise, and then we can build up the spectrum of a cosine. We can talk about time delaying a delta function and make use of that as well. So we get a lot of cool things that come out of this, and a few more things that I'm going to show you in 5 more minutes. I guess whatever I can get away with for the 5 minutes that remain. One of the things we can stop at, though, is something called the reciprocal spreading property, which is just a concept that you've probably seen before. I think it's in the review section of chapter 2. A signal that has 0 time width is a delta, and that becomes a constant spectrum. It covers all spectrum with the same amplitude A. And a signal that has infinite width, like a constant signal from minus plus infinity, it has 0 width in the frequency domain. So that's called reciprocal spreading. So you can always do that, even if it's got a finite time domain width, it will have some width in the frequency domain, and then if you let the time get longer in the time domain, it will get more compressed in the frequency domain, and then vice versa. So short pulses tend to have wide spectra, wide pulses tend to have compact spectra. Does that make sense? Just the idea is reciprocal spreading. So now we can take and consider the Fourier transform of periodic signals. So take the Fourier series representation for a signal and then go ahead and Fourier transform that term, but this is going to allow the Fourier transform and the limit idea to operate, so we're going to move it inside that doubly infinite sum, and each one of those complex sinusoids becomes a frequency shifted delta. So what we're saying right now, and this is valuable in the lab 2, is that the spectrum of a periodic signal can be expressed by locating the spectral lines with the delta function, and the amplitude, complex amplitudes, are given by the Fourier series coefficients. You're supposed to say, that's great, that's kind of nice to be able to do that. And it's all based on the Fourier transform and the limit idea. There's more stuff coming, but okay, so what do we have right now? We have, what's the difference between line spectra and continuous spectra? I say none. If you're taking a periodic signal, you can either use the line spectra idea that we've been talking about for Fourier series, or if you want to just use the Fourier transform and the limit, you're going to locate the spectral lines with the delta function in the frequency axis. I prefer thinking of it as a delta because it's just a lot more natural. When you take a Fourier series representation, you have that x of n, and you have to say, okay, x1 is going to sit somewhere, and I have to go and say, well, what's the fundamental frequency, and what harmonic am I talking about to actually locate it on the line spectra axes. Whereas mathematically, if we do it this way, the delta function automatically places the spectral line on the frequency axis. What do you think? I mean, that's what I'm telling you. Does that seem nice? I mean, there's really no difference. It's just that I like the delta function better because it locates the spectral lines in math. You plug a signal into a spectrum analyzer, it doesn't think that way. It just takes the waveform, and it does a time averaging technique in a sweep generator. I guess time is just about up, but I was going to tell you sometime how the traditional spectrum analyzer works. It takes a signal, suppose it's a 10 megahertz sinusoid, and how does it display that on the spectrum analyzer? So the spectrum analyzer has a sweep generator running, sweeping from over a range of frequencies, and then that sweep generator is producing a sinusoid that's mixing the signal or multiplying the signal with the input signal. And when the two signals are the same frequency, we come out of that multiplier, and this is where mixing action comes into play. We're going to get a difference frequency at 0 hertz, and that goes processing through a video amplifier, a narrowband low-pass filtering amplifier, and then we can have an envelope detector on that to get the energy or the power that's actually through a diode envelope detector in that signal that gets converted to 0 hertz. The sum frequency is eliminated when we do cosine times cosine. We get cosine sum, cosine difference. So as the oscillator sweeps along, it's just taking all of those signals that are at high frequencies, and as they individually, as you sweep on through, as they convert through the difference frequency down to 0, those get detected and create a deflection on the display, and the display is calibrated to follow, the axis of the display is following the action of the sweep generator. And then you're controlling the bandwidth of what you see through the resolution bandwidth, which is the bandwidth of the video, and so on. That kind of makes sense? I could show you a block diagram, but it's not a Fourier transform. It's a very kind of a conventional signal processing function, or actually communications theory idea. We'll talk about mixing and up and down conversions later, but that's where that's at. A new assignment will be coming out. This picture here is using the theorem to say this other property, Fourier transform of an impulse train, is an impulse train in frequency. And then we'll get to this theorem here, which says any periodic signal can be Fourier transformed using one period of the signal. And that was kind of the motivation behind that homework problem number 2 you worked, where you were just generating one period and then using the FFT to get the spectral lines. If you're wondering where all this is going, well, you need this background in order to understand modulation theory and communications. It's just kind of common sense stuff. And pulse trains, other things, they formulate the basic radar signals that have been around for forever. Send a burst of energy, shut it off. That's where the pulse train comes in, and listen for the reflection coming back from all of the terrain. So does that make you understand the pulse train, why it's so important? It's fundamental. You get interrogated by a pulse train of RF, and then your signature is how you reflect the RF back to the receiver. Or I'm thinking of police radar now, or the newest thing I think I saw on the news last night is that now those intersections that have the cameras, I think they've now turned them on, haven't they? Didn't I catch something in the news?
Like you talking about the stoplight traffic
Yeah.
stop sign? Yeah, they've been on for months.
Have they been on?
Yeah, the first like 3 months that or the red light cameras.
Yeah.
Red light cameras. Yeah, the first 3 months they were on, they raised like $600,000.
You don't find out for a week or so though,
Yeah,
right?
no, it takes some time.
Yeah.
Because in order for it to be legit, they have to have a 5.0 actually look at it.